Hello everyone, welcome back to another video on quantum field theory. In today's video, we will be going over the famous Maxwell equations. This is probably the most famous equation that we are going to go over in this series because the Maxwell equations represent a core aspect of classical electrodynamics. And using classical electrodynamics allows us to build electric devices, which powers homes, which gives us smartphones and all these cool things. So that's why the Maxwell equations are pretty famous. And another famous aspect of the Maxwell equations is that they can describe light. So they can describe the propagation of light. Now, here is the usual form of the Maxwell equations. And I wrote this out from memory, so they might not be exactly correct, but it's about correct. And the Maxwell equations, they just tell us that if we have some initial configuration of the electric field, what will the magnetic field look like? And they also tell us how these electric and the magnetic field dance together and how they change over time. So that's the basic idea around the Maxwell equations. And each of these equations stand for some important law. This is Faraday's law. Here we have Gauss's law, all these cool kind of things. And they're all covered in classical electrodynamics. So this is the usual form of the Maxwell equations. However, we can also write it down in tensor form. We first start out with the Maxwell Lagrangian. And here we see that we have the Faraday tensor over here. Now the Faraday tensor encodes the components of the electric and the magnetic field. So the Faraday tensor, if you actually write it out, it's like zeros along the diagonal. And the components of the Faraday tensor everywhere else are just the components of the electric and the magnetic field. So once we put this Lagrangian into the order Lagrange equation, we get this over here. And this is the Maxwell equation. How cool is that? We are able to write these four complicated equations into one very simple form. And the reason as to why we can do that is, again, this Faraday tensor, it has components of the electric and the magnetic field. So it's just basically just compressing all of these equations into just one line. And it is this form of the Maxwell equation that we will use. Notice I called the Maxwell equation because it's one equation, but it does stand for multiple equations since, again, we have a hidden summation due to the Einstein summation convention. All right. Also, notice that the Maxwell equation is just the case of where m equals 0 for the Procca equation. And I want to really stress this out because it's gonna help us throughout this video. Because remember that the Procca equation says that this equals m squared times a rho, where a rho is the EM vector potential, right? But since mass equals 0 for light, this term just drops out to being 0. So light does technically obey the Procca equation, but in general, for the case where mass is not 0, light will not obey the Procca equation. But for the case where mass is 0, it will obey the Procca. Wait, I don't know if I said that correctly, but just basic idea is that light obeys the Procca equation for the case where mass equals 0. In fact, the Maxwell equation is the Procca equation for the case where mass equals 0. With all that said, let's actually begin. So, how can we actually solve the Maxwell equation? Well, when we were solving the Procca equation, what we did was we took the partial derivative the partial row derivative on both sides, so with respect to like some x row parameter. And this was for the Procca equation, by the way. And we found through the Lorentz condition that this term on the left just goes to 0, which means that 0 equals this over here. We then divided both sides by m squared to get 0 equals partial row a row. And this is a continuity equation. And we just plug this equation into the second form of the Procca equation, which was this over here. So you just plugged it into the second form where we expanded the Faraday tensor. And by plugging it into the second form, we then got the Klein-Gordon equation. And from there, we can use an ansatz for a row, where a row equals some vector times the plane wave solutions. And that was how we solved the Procca equation. So basically, all we really want to do is try to show that partial row a row equals 0 for the Maxwell equations, and then we're basically done. Everything else just comes out naturally. So as long as we can find that continuity equation, then we've hit the gold pot. So that is what we actually have to do. So how can we actually do that? Well, let's just repeat the same steps, but for the Maxwell equation. So for the Maxwell, or let's use the same color. Well, not color, same thing, but white instead. So for the Maxwell equation, let's just take the derivative on both sides with respect to rho. Oh, remember that there's no mass term, right? There's no mass term. And the Lorentz condition implies that this entire thing goes to 0. So we get 0 equals 0. What? Well, yeah, it's true that 0 equals 0, but that doesn't really tell us anything. Like, if it said 1 equals 0, that would be pretty bad, right? Since it means that there's a contradiction. But 0 equals 0 is true, and that doesn't tell us anything interesting. So the trick of multiplying both sides by some derivative doesn't really help us very much. So clearly, we cannot use that trick to solve the Maxwell equations. So it seems like we are out of options. So what can we actually do now? Well, this is where gauge theory comes to save us. Gauge theory. Now, what is gauge theory? Well, gauge theory is essentially the study of what are called gauge transformations. So in physics, we tend to use transformations quite a bit. For example, in my 2 videos on Noether's theorem, we talked about transformations that look like x is transformed to like x plus a, where x is just some space-time position. And we talked about how transforming our position will change the physics, or might change the physics of our system, right? So typically, when we transform coordinates or momenta or whatnot, our system will change in some way. Now, when we actually transform our quantum field itself, that's called a gauge transformation. So for example, for the scalar field, let's just use the vector potential, since that's relevant. If we were to transform a rho into a rho tilde, the transformation is called a gauge transformation. Now, technically speaking, it's only a gauge transformation if it's local, but that difference doesn't really, well, it's not very significant. So for our purposes in this video, any transformation on the field itself is a gauge transformation. Gauge transformations are also called internal transformations. Now, if our gauge transformation leaves our Lagrangian invariant, we call that a gauge symmetry. So if L equals L prime, or better said L tilde, we say that we have a gauge symmetry. And if our gauge transformation leaves the Lagrangian unchanged, this is going to imply that the equations of motion for our system will be the same, since the Lagrangian controls our equations of motion. So I'll reiterate that. If our gauge transformation leaves our Lagrangian unchanged, that means that our equations of motion are going to be the same. This is a very important point. So, what gauge symmetry leaves our Lagrangian unchanged? What gauge transformation leaves our Lagrangian unchanged? Well, it turns out, let's actually write down our Lagrangian for reference. It's L equals minus 1/2 F mu nu F mu nu. It turns out that the gauge transformation of A to A tilde, where A tilde equals A rho plus partial mu f of x, this gauge transformation will leave our Lagrangian unchanged. Here, f of x mu is just some random function on spacetime. It can be anything we want to. It can be any function. Like, it could be, say, I don't know, e to the 3x mu or something. It could be x mu plus 1. Any function on spacetime. And this gauge transformation will actually end up leaving our Lagrangian unchanged. Now, if you guys don't want to believe that so soon, you can actually try this yourself. Plug in this gauge transformation into our Lagrangian, and you'll find that L prime equals L. It's a pretty straightforward calculation, so I won't cover it. I won't actually show it in this video, but it's pretty straightforward. Just expand the Faraday tensor in terms of the vector potential, and then just substitute the vector potential with our gauge transformation. And then show that the new Lagrangian reduces to the old Lagrangian, which implies that we have a gauge symmetry. So, yeah, this symmetry, this transformation is what is called, leaves the Lagrangian gauge invariant. So here is our gauge transformation, and this transformation will leave our Lagrangian unchanged, which means that we have a gauge symmetry. So, what was I gonna say? Yeah, so this over here, this term over here, we like to call that term a gauge. So that's just some extra terminology to memorize. We call that a gauge. So we just add a gauge to the old field to get the new field. So Again, with coordinate transformations, like in physics, by choosing different coordinate systems, it can make our physics a lot more easier, right? The same thing with gauge transformations. You can choose a gauge or fix a gauge such that the physics becomes much easier to work with. The same thing applies here. So we can choose a gauge such that partial rho a tilde rho equals 0. That's a pretty sneaky trick that we're doing here. We're fixing a gauge such that we have this relation. And this isn't, again, using a gauge isn't very bad, since even though our new field is not the same as our old field, remember, A tilde is not equal to A rho, but the dynamics of the field will be the same, since the Lagrangian is the same. So we can work with the new gauge without having any problems concerning the dynamics of our field. So, yeah. So we can just choose a gauge such that we have that continuity equation. Yeah, we couldn't really find it. It's kind of a cop-out move, but it's the next best thing. So the question remains, what gauge can we use where we have this relation? Well, to do that, we just have to plug in our gauge transformation, which is just a rho plus this. We just expand this derivative, or distribute this derivative on the inside. And this implies a partial of this equals negative of our gauge with some derivative. So now we have arrived at this equation. By solving this equation, we can find what gauge we have to use. What gauge we have to use in order for us to have this continuity equation. But we're physicists. We don't like to solve equations when we don't have to. Well, it can be fun. But in this case, we don't actually have to solve this equation. As long as we know that a solution exists, we can just jump straight into using this equation over here. So what I'm saying is, as long as we know that some solution exists, there exists some gauge such that we have this continuity equation, we don't have to know what a rho is. We don't have to know what our gauge is. As long as we know that there is some gauge that allows us to deal with this, we can just jump straight into dealing with our continuity equation. We can just sit comfortably in our chairs and know, well, I don't know what the gauge is, but I do know that a gauge exists. So I can just use this. Sure, I don't know what it is, but it tells us that we are allowed to use the continuity equation. So with that in mind, we can just use this equation without actually knowing what the gauge is. Some people might say, well, that's kind of a cop-out. I would be one of those people. I think we could solve this equation, though. But it allows us to calculate things faster. So let's just jump in and start using this continuity equation. And this is actually called a Lorentz gauge, by the way, for those that might want more information. We use the Lorentz gauge to get our continuity equation. So we now have this continuity equation found here. We're going to relabel a rho tilde to just a rho, just because it's visually nicer. Let's just keep it in the back of our heads that we are dealing with a transformed field here. So we can just plug this back into the Maxwell equations. And by doing that, we will actually derive the Klein-Gordon equation, which states this over here. It's just the same steps that we took in the first Praka equation video. So we get this relation over here. This actually is just the Klein-Gordon equation for the case where mass equals 0, since we are dealing with a massless gauge field, the gauge field being a rho. Also, by the way, we call a rho a gauge field because reasons. So, I mean, the reason is, actually, don't, well, the reason will make much more sense once we get into gauge theory, which is going to be the next 2 videos, or the video after this video. So, wait, no, it's the video after this or after this. Who cares? So, here's the equation over here. So let's expand this equation out a bit in order for it to make a bit more sense. So remember that this stands for a summation, the summation being partial not minus this summation over here, a rho equals 0. We can just choose the case where I is only equal to 1 in order to make this simplify it a bit more. And then we can just write our derivative sign in a bit more explicit form to get this equation over here. So this is much more easier to work with, but you can also work with this. In fact, we will work with this shortly, but I just want to write this in a bit more clear way for those that might not be as comfortable with the tensor notation. So this is just what this thing over here is trying to say, just in a more compact form. And this is a standard equation from calculus. It's a homogeneous differential equation. It's also multivariable, so we can just solve this differential equation by using. Sorry, I'm talking way too fast. We can solve this differential equation by using what's called separation of variables. So we can just write a rho of like xy, or not xy, of tx as some purely temporal term times some purely spatial term. And we actually do that in tensor form by saying that a rho equals a rho equals the vector times e to the minus ik mu x mu. Since e to the ik mu x mu is just equal to some spatial term times some this doesn't make this works times some temporal term times some spatial term e to the ikx. So we can use this as an ansatz, since this is just the Klein-Gordon equation, right? And we know that the equation is built off of plane waves, so we can just use a plane wave ansatz, and we can then put in our polarization vector over here. Also want to note that a rho, this is a 4 vector, by the way, so technically speaking each component satisfies the Klein-Gordon equation. So we can check that this is indeed a solution by just putting it in our Klein-Gordon equation. So we have this. We should have. Actually, I don't need parentheses here, really. This equals 0. We can then just distribute our term and take the second derivative. That's just going to be equal to minus k sigma. So this implies that k sigma equals 0. This is just the mass on shell condition for a photon, right? Since we know that k mu should equal m squared, But since m equals 0, this implies that k sigma is just going to be equal to 0, right? So we can use that condition, and that does mean that our solution is satisfied. Since if this is 0, this entire term is 0, so we get 0 equals 0, which is true. Okay, so what did I just do? Oops. This iPad it's a new iPad. It's pretty weird. Anyways, yeah, that's our answer. That's our solution to the Maxwell equations. It's this over here. We can actually put this into our formula for the electric and the magnetic field, even the Faraday tensor as well. So you look to find out how those fields will look like. So we can just, again, plug this into other expressions to find formulas for the electric, magnetic, and the electromagnetic field. So there's still much more to do, actually. We still haven't found out, well, technically speaking, we're done. We just solved it right now. We should have this should be a function of x, by the way, or a function of space-time events. So we're done. This is our answer. And in the next video, we will actually be talking about constraints on the polarization vector. So yeah, we're done. We solved the equation. All we have to do now is find out what constraints we have on our polarization vector. And that's going to be the next video. So I'm going to cut this video off a bit short, and we will talk more in the next video. So thanks for watching. I hope you guys subscribed. I hope you guys like this video. If not, tell me why you don't like it, and I will value your feedback. Alright, until next time, guys. Bye.